Okay, let's get started. Sure, go ahead.
Okay, good afternoon everyone. Today I'll be talking about discovery in self-organizing hierarchical ad hoc wireless networks. And to just give you an idea of what I'll be talking about, first I'll introduce the problem of discovery and what we're trying to solve. Then I'll talk about the hierarchical architecture for which specifically we've handled designing the algorithms. Then I'll go into an analysis of centralized topologies in terms of energy, delay, and throughput considerations. Then I'll move into distributed algorithms for achieving these topologies. And then simulation results comparing our centralized and distributed algorithms. And finally, I'll talk about a prototype that we've implemented at WINLAB. So just to give you an idea of the scope of the problem, if you take a typical ad hoc network, the protocol stack would look something like this. I'm just showing part of the protocol stack from the file layer to the network layer. So basically what would happen is the file layer would set the transmit power to a certain value, and then based on this transmit power, whichever nodes are within range, they'll be sharing a medium at the MAC layer. And then what the network layer does is exchanges routing information with all nodes which are within transmission range. And so in a network without discovery, what would happen is a topology is something like this, where if the transmit power is high enough, every node can hear every other node and exchange routing information with every other node. So it's a very dense topology, and it leads to a network with high routing overhead. So what discovery would do essentially is sit between the MAC and the network layers. And the idea is that whichever nodes that the MAC layer can hear, what the discovery layer would do is process information about these nodes and decide that only a subset of them are useful. And then it will only allow the network layer to interact with nodes that the discovery layer decides are good. So in such a case, you see that, for example, here we can form a topology which is much more sparse, and this can control the routing overhead to a considerable degree. So what I've shown here is a very abstract view. So these are just a few wireless nodes, and each of these links represents a wireless link. So basically the idea of discovery is to control the topology and then form the network in a way which is useful in terms of the objectives, such as minimizing the energy or delay or maximizing throughput. Yeah.
Do you think that you're adjusting transmission power?
So there are two forms. One is reducing the transmit power to control the number of neighbors. The other is even at a certain transmit power, we can still reduce the number of neighbors we're interacting with. So we can only consider a subset of neighbors as useful. So let's say if energy is a consideration, you would only you can talk to only your nearest neighbor, for example. Okay. So the motivation behind this, as I said earlier, is to control the routing overhead of the network and to form the topology without waiting for the network layer to form the routes explicitly. Again, the aim, just to summarize, is to develop a distributed neighbor discovery protocol. And the idea is the protocol should form a topology which is good in terms of energy, delay, and throughput. And for our work, we specifically considered an 802.11 based hierarchical network architecture, which I'll be talking about in the next few slides. Okay. And in order to design our protocol, the first thing we do is study the topologies from a centralized point of view. And then based on our observations from the centralized scenario, we will then develop distributed algorithms. And to describe the basic architecture that we considered, we look at a three-tier hierarchy where the lowest tier is the mobile node layer. These mobile nodes are generating data which is destined for some location on the internet. So basically there's flow of data from the mobile nodes to and from the internet. And these mobile nodes have a single wireless interface. And to reach this internet, which is through on a wired network, we have the highest tier called the access point. these access points are gateways. They have one wireless interface to connect to the mobile nodes and one wired interface to link to the internet. And there is a third tier in the network, the intermediate tier called the forwarding node. The objective of the forwarding node is basically to extend the coverage of the network. And these forwarding nodes have two wireless interfaces each. So that would mean that they can talk to the MN layer and the access point layer simultaneously. And the idea here is that the MNs are low-power nodes, and they would like to conserve energy. That's one of the constraints there. They are low computing power devices. So what would happen in this hierarchy is that the mobile nodes would not participate in the routing protocol. Their basic idea is to reach either a forwarding node or an access point as quickly as possible. And then, even in order to communicate with another mobile node, a mobile node would have to use an intermediate forwarding node or an access point. It cannot talk to an MN directly. So this is how the protocol stack would look at each of these nodes. Like I said, the access point has one wireless and one wired interface. So this part of the stack corresponds to the wired segment, and this for the wireless. So basically, you can see that there is a discovery sublayer in the protocol stack which is responsible for forming the topology of the network. Similarly, at the forwarding node, which has two wireless interfaces, again, the discovery is present. And just to mention the mobile node specifically, since the mobile node is the one that's either generating data or receiving data from the internet, we have an additional application running on the mobile node.
So you're assuming in your hierarchical network that traffic can be both directions, going up and down?
It can. But the flow is vertical along the hierarchy. That's what we look at. So it will be something like a person trying to access a web page, or a sensor network where the sensor is reporting data to some location on the internet. It's that kind of
specifically, I'm asking because the sensor network, there's not as much need for it to go down.
Yeah, right.
Here you are allowing for it to go down.
Sure. In the simulations that I've run, I've basically considered data going upwards, but there's no restriction as such.
Right.
So just to give an idea of the other work that has been going on in this area, there has been work in the field of power-aware routing. One of the first works to come out was by Raju and Meng in 1999. So there the idea is they developed a mathematical model for forming the topology. So the idea there is to decide which nodes will forward your data. And so in order to do this, they used GPS receivers so that the location of neighbors was known. The next work was by Ramanathan and Rosales in 2000. So there the idea was to develop distributed algorithms using transmit power control. But the idea is to keep the number of neighbors between certain limits, not too high or not too low. And another related work was in power control and clustering by Kavadia and P.R. Kumar in 2003. And here they developed first a protocol called COMPOW, where they say that in 802.11 networks, using a common power level for all nodes is a good idea in terms of reducing interference. And then they extended to a clustered network as well. So just an idea of the routing protocols. These are the three most popular routing protocols that have been in use in ad hoc networks. So DSTV is a distance vector-based routing protocol, and this is, as I'll be talking about later, this was a similar routing protocol was used in our prototype implementation. And AODV by Perkins and Royer, this is an on-demand protocol. The idea was used in our simulations. So AODV was the basis for all our simulations. And just to give complete coverage, I just thought I'll mention DSR or something related, but we don't use DSR in our work in any way. It's just that DSR also is a very popular routing protocol. So our discovery protocol is general enough to run in conjunction with any of these routing protocols. It's not limited to any one routing protocol as such. As I mentioned, we would like to first study the topologies from a centralized point of view in order to understand how the distributed algorithm should work. So, like I said, reducing the number of links with which a node interacts will certainly control the routing overhead, but we'd like to make sure that there is no adverse effect on the performance of the network in terms of throughput and delay. So, we use linear programming based models in MATLAB to generate these topologies. So each of these topologies will correspond to the centralized routing strategy. So it would represent the topology that would be used by a routing protocol when it has all the information about every node. To give you an idea of the trade-offs that are involved, this topology shows a few mobile nodes, forwarding nodes, and access points spread over an area of 500 by 500 meters. So the red triangles represent the access points, the blue circles represent the mobile nodes, and the diamonds represent the forwarding nodes. So in this particular case, the idea is to minimize the delay. So the objective of the network is to minimize the delay. Each mobile node would try to connect to the access point in as few hops as possible. One thing I should mention is that the delays we consider are in terms of number of hops. In this particular objective, each mobile node uses as much transmit power as possible, and then in a single hop tries to reach the access point. And this is actually what a standard routing protocol would use. A standard routing protocol tries to minimize delay. So this is how the topology would look.
So down there's a mobile node connected to a forwarding node connected to an access point.
Right.
So are there no? I mean, if they just want to minimize the delay, you're saying they're allowed to transmit at whatever power they want.
There is a limit on the transmit power. So in this particular case, the access point was out of range, so the mobile node went through an intermediate forwarding. So if we change the objective of the network now from minimizing delay to minimizing the energy, then the topology would look something like this, where now instead of blasting at a very high transmit power, each node would try to go to the nearest forwarding node and use multi-hop forwarding. So in this case, now you can see that particularly this mobile node, which was transmitting at a very high transmit power, now decides to switch to this closer forwarding node. Okay, and then use that to reach an access point. So now if we
treat interference.
I beg your pardon?
How do you treat interference in the model?
There is no interference as such. This is basically I use a simple path loss model to decide the transmit power and then try to minimize that. But it's not that nodes are actually interfering. It's
So there's no interference. Let's say those two blue mobiles going to one forwarding. So there's no interference between the terminals. So it's basically
right. Because the way I treat it, they're sharing the medium equally. So I assume this perfect map here which says they share the throughput equally, and that's it.
So the value given as far as energy is concerned, flow. Okay.
Okay.
One question.
Yeah.
Energy minimization only for the mobile nodes or for the forwarding nodes also?
So the idea here is that mobile nodes have high energy constraints. So I've considered a forwarding node energy cost.
Because here the forwarding node has to forward for all the three nodes in this case. So it uses up its energy.
Right. So I've considered the forwarding node power as being several orders of magnitude lower.
So constraint is mainly on the mobile node.
Yes.
Do you think the forwarding node is moving or fixed?
Actually, since this is centralized, I'm just looking at something like a snapshot. But later in my distributed simulations, I do consider forwarding nodes to move. Yeah. The idea is that forwarding nodes can move to change the coverage of the network. So now, if instead of minimizing the energy, we change the objective to maximizing the throughput. Now, like I was saying, so in this case we consider that throughput is shared equally. So when we try to maximize the throughput, it is basically like balancing the load among the access points. Okay. So For example, in this case, you have more mobile nodes going towards this access point. So when you try to maximize the throughput, some of the mobile nodes will now switch to this access point to balance the load. But in a network, especially where if you look at a scenario like a sensor network, the idea is rather than worrying about things like minimizing the delay or maximizing the throughput, what you would like to do is, let's say, minimize the energy of the sensor, but without causing too much of a delay, or without reducing throughput too much. So what we considered then was the objective where you minimize the energy, but you have a constraint on the delay of the network. Okay. So in this particular case, these two plots show the same nodes in a certain area, but over here the idea is the nodes minimize the delay, but there is a delay constraint. They minimize the energy, but there is a delay constraint of 3 hops. So a node can form a link to the access point as long as the path is not more than 3 hops in a delay. Okay. And this particular case is where the nodes try to minimize the energy, but the delay constraint is 2 hops. Okay. So, for example, in this particular case, this mobile node is using a path which has 3 hops: one to this forwarding node, another to this forwarding node, and finally to the access point. So this particular path is 3 hops. But now, when the constraint changes from 3 hops to 2 hops, this is no longer acceptable. So now this mobile node uses this path where this forwarding node, instead of going through this intermediate forwarding node, it goes to the access point directly. Okay, so now the path has changed from this 3-hop path to a 2-hop path.
I think it would be useful if you put out the equation at this point to show people how that optimization was achieved.
Yeah. So in either case, it uses this forwarding node instead of using the other forwarding node.
Exactly. In fact, that was.
Right. Yeah. So okay.
So the idea is, since the constraint mobile node is higher, the idea was that the mobile node goes to its nearest neighbor, and the forwarding node is the one that's responsible for constraining.
The algorithm for mobile node is to go to the closest forward.
Exactly. That's what you came up with.
These are also centralized.
No, that is not. That's not the algorithm. Why don't you show what the equations are?
Okay.
You can have a heuristic like.
Yes. So in the centralized case, this is the objective. What these equations are essentially trying to do is, for each node, you try to minimize the. I think it's just trying to draw this. So if we have one access point and forwarding node and a mobile node. So basically, each of these is either a 0 or a 1. Okay, each of these links is a 0 or a 1. So that means this particular path is chosen if it is 1, and this is not chosen if it's a 0. Okay, and the idea is over a whole network. Actually, we just consider this. Yeah, we can just consider 2 forwarding nodes. So this mobile node can either go to this or this forwarding node or this forwarding node and reach this access point. Okay. So so you either select this path or this path, and similarly either this path or this path. And what the objective is trying to do is minimize the sum of these. So we consider a Pij for each of these links, which is the power cost of each of these links, and we minimize the sum of these links. Okay, and in order to make sure that there is sensor data going from the mobile node to the access point, we have these flow conservation constraints. What this expression is trying to do is say that for all intermediate nodes, such as these forwarding nodes, the sum of flows through these nodes is 0. Okay, which means that there is no data ending at this point. Then what this expression is trying to do is make sure that there is data going towards this particular node. Okay, because this is basically the difference between all flows inwards and all flows outwards. Okay, at the access point, since that is the sink of all the data, the sum should end up as the total of the data that's going through. Okay, and this particular constraint is essentially trying to say that the sensor is the source of all the data. Okay, and we have an additional delay constraint which says that the sum of all these hops should be less than n hops. Okay.
So you are concerned with the power of all of them or only the mobile nodes? Which one?
Like I said, the main minimizing the power comes up at this mobile node layer, but I do consider the power at the forwarding node. It's just that the cost is 100 times lower at the forwarding node.
But I guess power from the viewpoint of mobile node doesn't really matter which way you go. Does it matter?
I'm sorry?
From the viewpoint of the mobile node, does it really matter? Does it matter which way you go?
You mean whether you go to this forwarding node or this forwarding node? Well, since this forwarding node is at a much greater distance, you will need to use a higher transmit power to reach that forwarding node. So, in fact, if this mobile node goes to this forwarding node, it can save by using the lower transmit power.
So, what kind of protocol are you using? What kind of protocol are you using?
So that this is centralized.
So
this is a centralized mechanism, but we just like to see the topology that, if we were to translate these into a real system, basically.
So you are basically adjusting the power to the distance.
Yes.
In this. So are there any of the protocols studied?
Several works actually do use path loss as a measurement. Like I said, Raju and Meng, that was one of the first works on in this area. So they consider this path loss, and then they take a certain transmit, using a higher transmit power is required to reach a higher distance, a longer distance.
So where do you get that? I mean, distance. How do you know the distance?
Since this is a centralized look at the topology, I know everything.
You will talk later. You're going to describe a distributed scheme editor, so why don't you tell him that? Yeah, go ahead.
Sorry, I will talk about the distributed editor.
This is just an idealized model to get the upper bound.
Yes.
So how are the powers determined to guarantee certain packet error rates? What's the
this? I basically consider the free space propagation. So it's just something.
So guarantee some.
Think about purpose. In this point, it doesn't consider error. It's just mission.
So you suggest that it's quite a power.
And if you take a spec, 7 dB SMR in the receiver, this is can be that. Wow.
Go ahead.
How you solve these equations? So basically, you use a dynamical programming.
Actually, MATLAB provides a linear programming model for that. So we just translate these into the right matrices and then provide that to MATLAB. So that solves this problem. Go ahead. So similarly, we also consider minimizing the energy with a throughput constraint rather than a delay constraint. So again, so this particular topology shows a minimum energy topology where there is no constraint. So there is no need to balance the load between all the access points. So in this particular case, you can see that only these two mobile nodes are going towards this access point, and all the other mobile nodes are going to this access point because that is the minimum energy path for them.
Here, when you see this throughput constraint, right? So you have some assumptions will say, and the link between forwarding node and access point
has a higher bandwidth or something like that?
No,
because your access point is a bottleneck, right? So whenever you do the load balancing within your ad hoc network, it doesn't matter. So it's all the traffic goes to your access point. If you have all the links has the same bandwidth, right? So it's, you see what I mean?
So yeah, I think I understand. So basically, it's these forwarding nodes have two wireless interfaces, so they can operate on two different channels.
Right.
Right. So which would mean that this uplink to the forwarding node is not contending with this link from one forwarding node to another, or for example, from the forwarding node to the access point. So, but yes. Basically, what this is saying is the amount of the throughput that you can get from the network depends upon the number of the access points, because that is your entry point into the internet. So yes, certainly. So the idea is to distribute as much as possible between these access points, because if you have 100 mobile nodes going to one access point,
then you have two access points.
N. Okay. Right. So I'm just showing this because it's easier to explain with a fewer set of nodes. That's all.
You want to show the equation for this case?
Certainly. So this is the objective for the throughput. So now instead of a 0-1 flow, we now have a flow which can be anywhere between 0 and the maximum data that is being offered to the network. So again, what each of these constraints is saying is this particular constraint says that the data, the sum of flows through intermediate nodes is 0, which means there is no flow ending at a forwarding node. And this particular constraint says the total data going to the access point has to be the sum of the offered load from the mobile nodes, because that is the sink. And since this particular constraint says that all data starting from a mobile node is non-zero. That is, the flow coming from a mobile node is positive. Okay. And in addition, we have this wireless medium sharing, where I'm assuming a TDMA kind of a thing. So each mobile node shares the medium equally.
Yeah. So there are say 5-6 mobile nodes. They transfer the data to a forwarding node.
Yeah.
So the forwarding node is at the center of two access points. So the forwarding node decides which access point it has to go to, right? Depending upon the load that an access point has at that moment.
That is a heuristic that's possible again. So that's what we find from.
Yeah.
Can I go back to the previous one? Okay. So yeah, again from this, when you have the throughput constraint again, so since the energy is the most important thing for the mobile node simply goes to a forwarding node, and it's a forwarding node. For example, in this case, it's this forwarding node which diverts some of the traffic to the other access point.
So how is there a number of access points? How does the forwarding node know what is the load on every access point at that instant to do the forwarding?
Yeah, this is centralized view. So it's basically like saying you know everything about each node. Okay. So now we move into the distributed part of section topology formation. So the basic idea of BEAD, which is Beacon Assisted Discovery Protocol, is that the forwarding nodes and access points are periodically sending beacons. Okay, if you look at a typical 802.11 network, that's what an access point would do. So the idea is to use this existing beacon and add some data to it. So we augment the beacons with some data, and that will enable the mobile node to decide which forwarding node or access point to connect to. Okay, so the mobile node, what it does is, once it hears the beacons from all the forwarding nodes and access points, it does an evaluation on the information. So this could be minimizing the energy. For example, if since the mobile node would like to minimize the energy, in that evaluation it can decide which forwarding node or access point is the closest. And then finally it will send an association request to the forwarding node or access point, and there will be an association response from the parent. Once that is done, this is where the topology formation phase ends, the discovery phase ends, and then the node moves into a route discovery phase where it will try to find a path to the destination. And finally, once it finds the route, it will go into a data transfer phase. In order to employ this distributed algorithm in NS, we had to make certain modifications to the node structure. So in NS, the basic node structure would involve just one part of this protocol stack, and particularly since the forwarding node, I'm just showing the stack for the forwarding node. So the changes that we had to make was, first thing is we had to add an additional link layer onwards to the file layer. Then we had to make certain modifications in the file layer to support multiple channels. And then for our beaconing, associations, etc., we had to add functionality to the MAC layer. And finally, the AODV in NS2 doesn't support multiple interfaces, so we had to add functionality for that as well. And then of course we had to define new packet types, counters, and timers.
Is this the forwarding node architecture? Or
yes, this is the forwarding node architecture. The mobile node and access point, they would, for example, the mobile node would not have this part of the node structure. And the access point would, in addition, have a wired interface instead of this.
They also don't have any routing for
the mobile node, yes. This is a dummy layer where, since the only job that the mobile node does is send to its parent, there is no routing there.
Forwarding node send out beacons from the two interface or just the one interface?
It sends out beacons on only one. So the easiest way to explain the forwarding node is it is an access point on one interface and a mobile node on the other interface. Okay. So on one interface, it's acting like an access point. It's sending beacons and it will receive associations from other forwarding nodes or mobile nodes.
So they operate different channels, right?
Yes.
And that's how the forwarding node find another forwarding node.
Like I said, the access point part of the forwarding node, that is always sending beacons on a fixed channel. So if another forwarding node had to reach this forwarding node, it would use that particular interface.
The forwarding node may form an ad hoc network, right? If that interface doesn't send out the beacon, then you have to use some kind of this routing discovery instead of link layer discovery.
Well, no, because since rather than working in ad hoc fashion, since it is continuously sending out beacons on one fixed interface, there is no need for an explicit route discovery on both interfaces, if that's what you're asking. So let me just explain. So if you have one forwarding node with two interfaces, okay. In fact, actually, I think a better way of representing this would be to say something like AP and MM. Okay. So this basically represents each forwarding node. So this is one forwarding node, this is another. So the idea is that the forwarding node is sending out beacons on this interface, okay, and it is scanning all the channels on this interface, okay. So it's scanning through all available channels through this. So similarly, this is also sending out beacons on this interface, okay, and these channels are fixed. So the FN would always send out these beacons on a particular channel. So now, when this forwarding node had to connect to this, since this is also scanning all the channels, right? So it would listen to beacons of this particular interface of the forwarding node. Okay, so that using this interface, it will record this particular forwarding node. So if this forwarding node had to reach this, this is how the link would look like.
Okay.
Then, what we did was we first wanted to simulate BEAD to obtain the parameters such as the beacon interval, the number of missed beacons that you can tolerate. So we ran some NS simulations with a set of 4 access points, 10 forwarding nodes, and 100 mobile nodes, spread out in an area of 1,000 by 1,000 meter grid. And we used, as I said, AODV as the routing protocol. And basically, just to summarize these results, because this is more to decide which parameters we should use for our main distributed algorithm simulation. A beacon interval of about 50 to 100 milliseconds, a missed beacon counter of 5, and a rescan interval of 5 seconds. These were found to be the best regions to operate in. Okay. Basically, in all our main simulations for the distributed algorithm, these are the parameters that we use. Just to summarize again, so for our simulations, we use a CDR kind of traffic where the packet size is 64 bytes, and the beacon interval is 100 milliseconds. We allow 5 missed beacons before we declare that the parent is lost, and then we go into rediscovery. And every 5 seconds, the node goes into rediscovery for this. What we did was we employed the minimum delay algorithm, which is what a standard routing protocol would do. So first, so each mobile node, instead of connecting to the nearest neighbor, it would just connect to the minimum delay neighbor. And we wanted to look at the performance of using BEAD with its hierarchical architecture over a network which did not have BEAD. And so for this simulation, in the network with BEAD, we had 4 access points, 10 forwarding nodes, and 100 mobile nodes. And in the network without BEAD, there were 100 mobile nodes. There are no forwarding nodes, of course, because there is no hierarchy. From these simulations, we found that using the hierarchy provides an improvement of about 2:1. So having evaluated BEAD as it is now, what we wanted to do was actually test out our distributed topology algorithms and compare them with centralized algorithms. So the distributed algorithms that we considered were the first thing is where each mobile node goes to its nearest FN or AP. So the idea is to minimize the energy at the mobile node. Then the second algorithm, just to compare, was minimizing the delay. So this is, like I said, what is used in the traditional routing protocol. So we just wanted to make sure it compares okay. So in comparing where the mobile node, ME is the algorithm where the mobile node goes to its nearest parent, and MD is where it tries to minimize the delay instead. So you can see that without compromising a lot on the packet delivery success, there is a considerable improvement in the energy consumption of the network, where the mobile node goes to its nearest parent.
But does it ever matter anything else except choosing the first link from the mobile node to the...
No. At the mobile node, since it is a low computing power device, we'd like to keep it as simple as possible.
I mean, so do you ever notice any other choice of I mean, anything else changing from the case on the left to the right, except just changing where the first link goes, first hop?
No, actually.
No, I mean, in the second, sorry, the first case you're minimizing delay.
No, actually, each of these lines
it's just showing 2 different things.
Right. So I should have explained that this graph shows the packet delivery success ratio for minimizing the energy and minimizing the delay at the mobile node.
Okay.
And this particular plot shows the energy consumption
while doing that.
Giving for each of these algorithms.
I see. But I'm asking you, okay, so maybe not with these. I'm asking you, you did simulations with 2 cases. One is when you transmit power minimization, the other is delay minimization.
Sure.
Do you notice ever any difference between these 2 except in the choice for the first hop?
Yes, subsequent forwarding nodes would also change.
Since they are like 100 times
yes.
higher power.
So right, so
it should be a really big difference.
Exactly. So there,
since difference.
Right. So at the forwarding node layer, basically, it's since they're trying to minimize the delay all the time, the energy is not a constraint. That part of the topology remains the same, and it's the mobile node which switches from one to the other.
This is energy consumption only in mobile nodes, or
yes,
all in the network?
No, this is just a mobile node energy consumption.
Actually, how does the mobile node knows how many hops you need to go to the access point?
Okay, so in order to do this, we extended the beacon to have an additional hops to AP. So there's a field which says how many.
So you extended the beacon.
Yes.
Okay.
I have a question.
Yeah.
So in one of the graph showed earlier, you said the throughput actually for hierarchy is twice of the flat. Why is that?
So actually the flat network loses out a lot because the uplink and downlink share the same channel, right? So whenever a node receives some data which it has to forward, first it has to receive and then it has to transmit. It can't do both at the same time. Whereas with the hierarchy, since there are two interfaces, that can happen in parallel. Okay. So certainly it's not an apples to apples comparison, right? But just to show you the benefits. So now what we like to show is the comparison with centralized algorithms. Earlier we had generated some topologies using LP models. So we would like to compare our distributed algorithm with what we generated using centralized mechanisms. So for this simulation, we considered a smaller network of 2 access points, 4 forwarding nodes, and 10 mobile nodes. And we considered also a smaller grid, 400 meters by 400 meters to ensure connectivity. And so now what this plot on the left shows is the x-axis is the packet, the offered load in packets per second, and the y-axis is the energy consumption at the mobile nodes in joules. So this particular plot shows the energy consumption of the centralized energy optimization, where the mobile nodes try to conserve energy. And for reference, we just plotted this, which is the centralized delay optimization. So this is what a typical routing protocol would use, since it's trying to minimize the delay. And this is the performance of our distributed algorithm. So you can see that the distributed algorithm certainly performs a lot better than the traditional routing protocol, but it also compares quite favorably with the centralized energy minimization. And the plot on the right, again, it shows the offered load as on the x-axis, and here the y-axis is the delay in seconds. So again, the delays of our distributed algorithm are do compare favorably with the centralized algorithm.
How in the distributed case, how do you know the distance between different nodes? Do you have GPS in each one of them?
No, we don't. Since these are NS simulations, what we do is we mark the transmit power in the beacon for every outgoing beacon, and when a mobile node receives this beacon, it reverse computes using the path loss and.
Why don't you jump to the beacon picture?
So actually this is a beacon that we transmit. So on every outgoing beacon, the node attaches a transmit power value, and for every received beacon, there is a received power that the node records. So this is how it can do it. So in NS, it's fairly easy because from the path loss models we can reverse compute that. But I'll be talking about this a little while later. So having shown that the distributed algorithm doesn't lose out in performance, that is, it compares well with the centralized algorithm, what we'd like to now see is the effect that it has on the routing overhead. Since I said at the beginning, one of the main objectives of this is to reduce the routing overhead, the information that's exchanged between nodes. And so this plot on the left shows the x-axis is the number of mobile nodes in the system, and the y-axis is the routing overhead incurred. The routing overhead is the ratio of the routing bytes to the total bytes sent in the network. And this particular plot shows the routing overhead incurred in a network without using discovery.
You mean every node, including MNs, participates in routing?
No, actually this is where it's just the forwarding nodes. MNs are still going there, but the routing information is exchanged between every node. So you can see that the routing overhead does increase quite rapidly, nearly exponentially, without discovery. And with the introduction of discovery, you can see that it's much more tolerant. It's a linear sort of an increase. Now, this particular plot has the routing overhead versus the node speeds. So the x-axis here is the speed of the nodes, the average speed of the nodes in the network. This is since the FNs and MNs are moving. So this is averaged over all the nodes, and this is the y-axis is the routing overhead in the network. Again, without discovery, you can see that as the speed increases, the routing overhead does increase considerably. Whereas with discovery, it's much more tolerant.
In your model, your FNs move at the same speed as your MNs, or because you have FN and MN mobilities are 5, 10, 20 meters per second.
Right.
Does that mean it's 5, 5?
Right. 5, 5, 10, 10, 20, 20. So yes, since I use the NS tools to generate the node mobility, it's a random baseline.
Right, but you didn't do anywhere the mobile nodes move much twice as fast as the forwarding nodes.
Unfortunately, I don't. So this was so far the work that I've talked about was mainly using MATLAB and NS. We also implemented a prototype of this network at WINLAB, and the basic mechanism again is as shown here. There are a couple of access points in the network, and just in this example, this particular access point is sending out beacons on channel 2, and this is sending out beacons on channel 4. These are just examples that I've chosen. And let's say a mobile node comes in, it's just turned on. So the way it would work is it would start scanning all the channels. So channel 1, it wouldn't find any beacons. Then it moves on to channel 2, where now this access point is sending out beacons, so it records this beacon. Then this particular metric, it records a metric. This is again a combination of this transmit power and receive power that I talked about earlier. Then what it would do is proceed to scan all the other channels, channel 3, channel 4, where it records a second beacon from another access point, and then it records the metric as 400, just as an example. So in this particular case, the idea is to maximize this metric. So it will send an association to that access point, and then it will start sending data. The metric that we used actually for the prototype was the signal strength of each recorded beacon. So these are the frame formats that we use in the prototype. Basically, our implementation was entirely at the application layer, since we couldn't have control over the MAC level beacons. So these beacons do represent the 802.11 frame, but there is some additional information. For example, the node type to show whether it's an access point or a forwarding node. And like I said, the transmit power on every outgoing packet. So every transmitter, before it's sending it out, it sends out a packet, it adds the transmit power. And whenever a beacon is received, the receiver appends the receive power. And this is an example of a neighbor table that is maintained at each node. So each of the elements of this beacon are then added to a neighbor table, so that the mobile node can keep track of all its available options. So the routing protocol that we used for our implementation, like I said, it's based on distance vector DSDV, and so each FN and AP periodically send out the routing updates with the current information about which mobile nodes are attached and which other forwarding nodes are within range. And since this is a multi-channel network, we need to also keep track of which channel a particular node exists on and the interface, of course. One of the additions that we had to add, I'm showing a protocol stack for the forwarding node. So since the forwarding node has two interfaces, each of these MAC interfaces would have a different MAC address. And to unify this, we use this concept of a node ID. Since we didn't want to work at the IP layer, we are doing it separately. We just use the node ID. And this is just an overview of the software architecture that we used. Each of these components corresponds to a layer in the OSI stack. So for example, layer 3 would be responsible for the routing information being propagated in the network. And similarly, layer 2 would be responsible for the actual beacons and other transmissions. Some experiments that we conducted, this picture shows a setup of 3 mobile nodes, 2 forwarding nodes, and an access point spread over 2 rooms. So we just tried to measure the throughput that we could get in the system. So in this plot, the x-axis shows the offered load in megabits per second, and the y-axis shows the packet delivery success ratio. So this is plotted for 2 different packet sizes of 1472 bytes and 1024 bytes. So as the offered load is increased beyond that the network can tolerate, you can see that success ratio drops.
So this is implemented using 802.11 card, so modified it.
We modified the driver of the 802.11 card.
So what do you do then? When you measure the distance, you adjust the energy, transmitting energy?
We look at the RSSI. So there is something called an RSSI that each card reports.
But do you adjust the energy, transmitting energy?
The transmit power.
Power, yeah.
Yes. So there are, in fact, standard cards support only 4 or 5 levels.
Oh, okay. So you play with those.
Yes.
So if you assume when you have a lower receiving power, that means that it's for the distance, right?
That is the assumption.
Okay, but what if? So you're assuming that only loss comes from the distance. I mean lower power.
Sorry? Yeah, that's right.
Well,
what if there are other sources of loss? Right?
No, so see, I think the point is that it actually doesn't matter when it comes. For all practical purposes, you need to spend more energy to reach someone who you hear, assuming the channel is reversible, right? Which is not necessarily guaranteed, but the problem is that.
So this
Beaconing tells you how far in radius space you are. It doesn't, maybe there are 3 walls and you're just next to, but there are 3 metal walls between. You can't reach that thing without expending too much power. So it's not, given that this is the ratio, right? Of transmitted power versus received power, or estimated received power. Therefore, it just tells you how expensive it is to talk to that other power.
That's really received power or SNR?
It's a ratio of transmitted power, the other way around, right? Received RSSI over transmitted power. So you have to take into account what the other guy is sending it. And you're assuming that it's reciprocal, it's reversible. Okay. So it's some estimate of this, if you want, but not necessarily correct. You're right.
Yeah, sure. It's not really physical distance.
No, it's not physical. It's not even the attempt to estimate the physical.
No, fine, I understand.
So to conclude, we presented a beacon-based discovery protocol, which the distributed protocol, which compares favorably with centralized topologies, and it provides a significant reduction in routing overhead. And we also described a prototype implementation that we have at WINLAB. And for future work, we'd like to study in more detail the interaction between discovery and the routing protocol. And finally, the idea is to integrate the MAC discovery and routing layers to work efficiently. And we'd also like to look into the trade-off between the robustness and the sparseness of the topology.